lunch. Good morning, lady and gentlemen. My name is Michael Kay. I'm the General Manager of FLEXCO in the UK. It's my great pleasure and privilege to introduce this year's Harold Wright Memorial Lecture. I knew Harold for several years through the MHEA, fascinating site visits, combative committee meetings and of course the conference. Harold was one of a kind. His passion for materials handling was legendary and very inspirational. A great advocate of applying maths and science to everyday problems and always striving for perfection and dragging our industry forward. I'd like to think that Harold was watching over us today, casting his critical eye over the proceedings and taking a particular interest in the next presentation, which is given in his honour, and on a subject which was very close to his heart, controlled flow for transfer chutes. So I'd like, if I could, invite my colleague Bernie Halpin up to the performance area, onto the stage. Bernie is the Managing Director of FLEXCO's transfer chute business in Australia. After graduating as a mechanical engineer, Bernie worked in a range of projects, in a range of project maintenance and operational roles at Collinsville, Curragh, Gordonstone and Gregory coal mines, mainly involved in the handling of coal and coal preparation plants. In 1998 he joined Queensland Sugar as their engineering manager for the 7 bulk sugar terminals, later adding the operational management responsibilities for Bundaberg and Brisbane bulk sugar terminals to this role. During this time with Queensland Sugar, he was responsible for delivering the Mackay ship loader project with a 400,000 tonne storage shed at Townsville. After working as unloading maintenance superintendent at TANNA coal terminal, Bernie joined FLEXCO as managing director of the transfer chute business in Australia in 2005. Over to you, Bernie.
Thank you. Apologies in advance. Apart from the accent, you've also got to put up with a croaky voice. So, also in the first of all, I suppose the formalities. Good morning, ladies and gentlemen. Firstly, I'd like to start by thanking the organising committee for giving me the opportunity not only to present at the conference, but also the Harold Wright Memorial Lecture. It's appreciated. Today we'll be discussing the history of our technology that we applied to the RG10 coal terminal expansion. And as Mike said in the introduction, I used to work at the terminal immediately before this expansion program got underway. So there'll be a mixture of we's. Sometimes it's Gladstone Port Authority, sometimes it's FLEXCO. What I was going to say is in the flash drive that's in your course notes, there is a white paper of this presentation which is a lot more detailed. So if there's interest in there, and having a read of the white paper document that accompanies this presentation. So FLEXCO transfer chutes, we design our chutes using Tasmanian technology. Now, the technology used at the RG10 expansion is what we call CFMTS. If we can just get that going there. Okay, we've got to thank our being an American company, we like to give things acronyms. So CFMTS stands for Control Flow Material Transfer Systems. CFMTS allows us to actually predict the flow path of material throughout the complete transfer process from discharge to receiving them. The concept, like anything, was this concept is focused on minimising energy loss in the transfer process. So at the discharge pulley, it's the maximum energy the stream has, and we've got to preserve that and get it onto the next conveyor. CFMTS is a mathematical model and incorporates a blend of fluid dynamics and vectors to predict the material flow. The material is treated as a cohesive body rather than individual particles interacting with each other. So obviously for this to be a valid method of analysis or design, we've got to keep the stream together. And the way we do that is by making sure that we minimise the impact angles in the transfer process. So, like I said, this whole analysis and theory is applied on the basis that it is a cohesive stream that we're moving, and it's applicable to free-flowing materials. It's not good for clays, it's not good for wet sticky ores, so it is the technology that we use for free-flowing materials. And we can evidence this minimal energy loss in the fact that we have minimal liner wear, there's low noise levels, and we greatly reduce belt top cover wear. So the mother of all invention is usually someone's problem, and in 1984 the development of this technology started in collaboration with the Glass and Ports Corporation, so it's interesting to be doing a presentation 28 years later in relation to, again, the Glass and Ports Corporation. The challenge at the time was to load 55-metre beam width ships that had just started coming to the port with a ship loader that was designed for 42-metre beams. GBC was having to turn ships at berth to fully load them, so they're going from a world-class facility to second rate. Alan Huth, as the operations loading superintendent at the time, had an idea. Standing beside the boom conveyor of the ship loader, he said, if we could just get out of the road of this stuff, I reckon I could get to the other side of the ship. Alan was a great operator, but he didn't have any technical background at all. So Paul Sundstrom from Tasman Engineers, was a forerunner for Tasman Warrajay, was engaged by the Port Authority. Okay, Alan's had this idea, is it going to work? So Paul embarked on a extensive literature search to see what was out there to try and describe the flow path of material through a transfer. And at the end of that search, he didn't think that there's anything out there that accurately did what we needed to do. So he, from a first principles basis, using the concepts of fluid dynamics, set about trying to describe the passage of a material, leaving a conveyor pulley and getting onto another conveyor, or in this case, into a ship's hatch. Paul was smart enough to write the equations, but he couldn't solve them. And luckily for us, we were able to get the local university, Central Queensland University, to solve the equations. So in 1984 and 5, the replacement ship loader telescopic chute work was designed. Longhand form, no computers, none of the software that we have available at our hands today. As well as that, the port wanted greatest flexibility they could get for their operators. They didn't want the operator having to drive close to the side of the ship's hatches. They wanted to park off and then articulate the loading boom forward, aft, seaward, landward to get in the corners of the ships. So it became quite a complex exercise. So the replacement chutes and the modifications to the boom were done in 1985. And here's a very grainy picture at the time. We didn't think we were preserving history at the time that this photo was taken. Obviously, we wouldn't be loading the ship with the boom this high, but it was done so that we could demonstrate the additional throw that allowed the ship loader to load the 55-metre ships. It's worked. The legacy of this first application, we now have 3 ship loaders utilising the same design, and the last one was built as late as 2007. So this innovative approach is what created CFMTS, and we're constantly being stretched to figure out what else we might be able to do, and that drives the development of the technology. And the original equations developed back in 1984 still form the backbone of a our software package that we've developed since that time. Just briefly, I'll need to describe some of the components that we'll be talking about today. Typical transfer system starts with a head of a conveyor. We talk about an inlet hood. I think these terms are common in industry these days, but at the time when someone sat down and said, what are we going to call this thing, we called it a hood. It's fundamental to the whole process. Gaining control of the stream as early as you can in the process allows you to do something with it. If you leave it too long, you've got less height, less room to work with. So the inlet hood collects, concentrates and redirects, gets that stream into a consistent shape and a direction. We know the cross-sectional area and the direction of that stream. So a combination, again, fluid dynamics and vectors, we know what's coming out of that hood and it's directed in the right direction for the next component in the transfer system. Okay. In a lot of the work that we do, and as people try to get more out of their plants, it's not just a simple one conveyor to another. You want to go from one conveyor to two or more. The next piece in the puzzle for us, we call them diverters or dividers. And I keep hitting that wrong button. And quite simply, a diverter directs or splits the streams to two or more receiving conveyors. We term them differently. A diverter goes one way or the other, a bit like a flop gate, whereas a divider actually splits the stream proportionally between two conveyors. What we say, they're inherently different. Of a flop gate has the partitioning device in the material flow. We all know what happens. The fines get in there, they freeze up. They invariably don't move in the middle of the night. Someone's got to go out there and flog them with a hammer to work. Whereas in a CFMTS diverter, we move the whole stream. It's a chute within a chute. So there's no material building up between the static and the moving elements of the diversion system. They hang them on a bearing, they're very easy to move, and allows us to online switch and split streams. And the last piece in every one, you've got to get it onto another belt generally, and that's what we call a loading spoon. And it simply collects what's delivered to it from a diverter or an intermediate chute, turns it and puts it on the belt at close to receiving belt strip speed. This is a bypass transfer on a stacker at a coal port, 8,500 tonne an hour, 5.2 metre a second belt. As you can see, that material, because it's just being delivered onto the belt at the same speed, it just lands on and keeps going. We are able to load directly to yard conveyors from stackers and reclaimers, no need for load tables, and being a maintenance guy, that's very attractive. Okay, I can end that one. So the last thing was just to say at the end of the day, we've got to package all this stuff, put it behind guards and for dust, and also to make sure that people don't get in harm's way. So a little bit about Gladstone Ports Corporation. It's a government-owned corporation which has, as you can imagine, comes with some baggage, but it's also very good because it has a mindset of serving the community, which allows companies like ourselves to get in and develop and work with them for the betterment of the local industry. It covers about 250 metres of 250 kilometres of the Queensland coast. Port Elmer in the north is roughly on the Tropic of Capricorn, the Port of Gladstone, and down to my stomping grounds down here, down to Bundaberg. It's Queensland's largest port, and the coal term we're talking about today has about 65 or plus 65 million tonnes of capacity. So in addition to that, there's another coal terminal, grain, bauxite, aluminium, and currently there's 3 LNG plants being constructed on Curtis Island. So it's quite a very busy port. Now the RG TANNA expansion that we're talking about today consisted of a 50% increase in their capacity. It was a two dump station, 2 ship loader terminal. So they're putting in a third rail receival, third ship loader, fourth berth. It's tidally affected, getting these vessels on and off a berth. They needed another berth just to park the one, having it in readiness for ship change. 5 new stockpiles were required to take advantage of. If you're bringing more in, you've got to store it somewhere. So there was 2 stockpiles up here and 3 in the foreground. 16 new conveyors were required to link the dump station and the new ship loader in. The original plan, which you'll hear about in the presentation, required 34 conveyors. We took 18 conveyors out of this plant by the application of our chute technology. The usual sorts of things when people are spending money, you want to get some cash flow as quickly as possible. So a short gain was seen to grab the shipping stream, speed those belts up and get from 4,000 tonne an hour to 6,000 tonne an hour on the 2 ship loaders that we had. That was phase 1. Then the stockpile 17 and 18, third rail receival station was planned after that, third ship loader, 4th berth, and then finally the 3 stockpiles down here. So our involvement with the project came after the existing shipping streams were sped up to 5.1 metres a second. Not particularly fast in Australian port terms. Most coal terminals are running between 5 and 6.5 metres a second on most of their belts. One of those vagaries, I suppose, I was working with a government organisation. The reason we weren't in here from the start was that we couldn't be self-sourced. The government regulation said you must get 3 competitive tenders. They couldn't find 3 competitive players, so the design proceeded down a traditional route. A range of engineering firms worked up packages, designed transfer chutes, tower structures, and then the Port Authority went out as the project manager and engaged contractors to build the works. So after the initial installations of the speed ups, they had a debottlenecking exercise trying to get the 6,000 tonne per hour upgrade to capacity. The first bottleneck was actually getting it off of the jetty conveyors onto the wharf, and then secondly after that, once they got on the wharf conveyors, trying to get it onto the boom of the ship loader. So this was the CC5 to CC6 transfer, which is from the jetty to wharf, as constructed by others. And in this particular application, the hood the output from this hood was a stream that was growing, shrinking, left, right. It wasn't consistent, and it was actually had what we call large rooster tailing, and eventually got to the stage that it would impact on the back, what would be the fines collection part of the chute. And as soon as you slow a stream down, volumetric equation, stream Q's the same, what's coming in is the same, but all of a sudden it's slowed, and then almost instantaneous blockages. So because the stream couldn't be properly redirected, it was slowed and it blocked anything above 4,000 tonne an hour. So, this didn't happen at day one. These guys have been fighting these bottlenecks for about 2 months before we got involved, and the ship queue had gone from a normal 7 ships at Gladstone to 40. So you can imagine the demurrage bill that was being incurred at this time. So the new 5 to 6 hood that we manufactured for the application got us the desired stream and shape. It was coming out of the hood at close to belt speed and a regular shape. We got a stepped input from 4,000 to 6,000 tonne an hour within a quarter of an hour of startup. And it didn't last very long because it lasted as long as it took for that to get to the ship loader. So we were successful in fixing this one and showing where the next weak link was. This chute looks particularly shiny because it was fabricated out of 316 stainless steel. The port couldn't afford a weather-related delay with painting. They wanted to fix it once and move on, and it's probably the most expensive chute that we've ever built. Wasn't expensive for the port when you got demurrage bills to pay. This is the originally upgraded shipper trigger to boom transfer. As you can see here, the original designer knew he was going to have problems. We didn't know what they were, but he put in some mechanism to control it. So he put an actuator on a curved deflector plate, put the remote controls for that in the operator's cabin. So if he's getting belt tracking or not loading properly, the operator could adjust that curved plate to try and get some steerage on the belt. As you can imagine, everyone would have had their own way of operating that curved deflector plate. And again, it was symptomatic of change the belt speed, or sorry, not change the belt speed, but change the tonnage. The deflector plate needed to be constantly moved to chase the tonnage. So what that deflector plate did, it slowed and misdirected the stream, gave lots of off-centre loading and mistracking and blockages. Okay, everyone that's worked on a ship loader knows that there's no room on board. You don't get heights for a transfer. You can't make it any higher. You make the tripper car longer. We lose stockpile capacity. We need more wharf. No one wants to make height to boom, elevated to boom transfer. But this was particularly problematic because the head pulley wasn't moved from its original position when the belt was sped up. So still the IP between that head pulley and the centre of the boom conveyor were the same as they were doing 4,000 tonne now. 50% speed increase, and it was still at the same place. So obviously a lot of impact forces in that transfer. So to overcome that, we installed a launch pulley, a control flow hood, and a soft loading double spoon. Because the stream was too wide to turn on one spoon surface, we had to split the stream and put it across two spoon surfaces. Now the reason for the launch pulley, it causes the coal to leave the belt, perhaps where this head pulley should have been positioned for the velocity of the belt. So the stream gets off the belt here well in advance of the discharge head pulley. That allows the stream to start to turn naturally under its own, under gravity, and reduces our impact angles on the hood. Reducing the impact angles, we don't slow the stream down, we maintain speed through the hood, and we essentially create more headroom. The other advantage that it gives is obviously we can keep cleaners closer to the IP point, because the head pulley is closer to the centre line of the boom conveyor. So that allows better value angles than, for example, had the head pulley been back here where it should have been for that belt speed. So happy days. Again, another shiny chute made out of 316 stainless steel, and we're able to get the ship loader up to 6,000 tonne an hour and softly loading. The next thing that was of interest to the port, by now they're a little bit gun shy that maybe all their transfer points could have problems. So they engaged a specialist consultant, materials handling optimisation, to have a look at their designs of their chutes to see if they might have any other problem areas. This particular CC4D is the third stream conveyor to collect coal from these stockpiles. The CC4E, the third shipping stream conveyor to get over here to our third shipping stream out to the new ship loader. So we had 18 reclaim conveyors. They were originally 1-on-2s to feed the two independent shipping stream belts. Needed to convert those to 1-on-3 transfers. So the original route that was planned for CC4E, as in this example, was on the ground beside the existing two shipping streams. Unfortunately, when you put it on the ground so far away, you can't get an acceptable chute angle from the head pulley of the reclaim conveyor all the way out to that third shipping stream conveyor. So the answer was, let's put in slew conveyors. Let's put in 18 of them across the site. Let's make them 1500 millimetres wide, because that's all we can string between the uprights of the existing transfer towers. So the plan is there's obviously there's 8 on this stockpile pad. There's another 10 on the other. So I was there at the time, and we were not looking happy days for maintenance guys, thinking 1500 millimetre wide belts, doing 6.5 metres a second, 50 metres long. It was not going to be a happy place to live. So we had these short, narrow, high-speed conveyors. To make the problem worse, we were going to have to construct roadways beside the conveyor, which were going to encroach on our stockpiles. We're in the business of moving coal, and we're losing stockpile space. So it was not a good solution, but I must admit I was one of the people there at the time. I couldn't think of anything better. So it was suck it up. We had to, this was going to be our life going forward. So in MHEA's review of what we were doing, they identifies an ultimate route, which would include a chute system. So FLEXCO was asked to confirm whether or not we thought it could work, which we did. MHEA, it was a good chute solution, but structurally, could we do it? So MHEA and a company called Aspect developed the conveyor concept that we said would work. So eventually we signed off on a new route that would work. So it's one of those meetings that I'll remember from my rest of my working life, when you walk into a project director's office and say, we know you're 3/4 of the way through your project, but we found a better way. And of course it was, that's good, but why didn't I know about this 2 years ago? At this stage, we was having this conversation. All the design work had been done. The original route for CC4E was finished. The foundations for all the slew conveyors were done. The long lead items for the 18 slew conveyors were procured. Gearboxes, drives, MCCs, pulleys, everything was on site. And the first slew conveyor was being put in on stockpile 18 at the time of our meeting. And we'd already spent $3 million getting to that point. And unfortunately for us, the alternate route was going to take longer to bring into play. Essentially because we were starting from scratch 3/4 of the way through the project. In credit to Gladstone Ports Corporation, Mark Greenaway, the project director, he said, he was the maintenance manager. He said, this is the right solution. I've got to take a long-term view, and made the right decision. There was a bit of a kicker in this though. We were going to save $7 million over the original design, and when you consider that $3 million had already been spent, it's plus $10 million saving. We got rid of 8 slew conveyors on those stockpiles. We negated those ongoing issues that people that work with short high-speed conveyors know about. We didn't lose 1 square metre of stockpile capacity, and the roads and drainage were unchanged. So there's a lot less in-ground civil works, and in a brownfield site, the last thing you want to do is dig a hole in the ground. So this is the one of the 1 and 2 transfers, is where CC4E was originally planned to go. So this bit of animation shows the original, very simple 1 on 2, what we call a seesaw spoon diverter. These were our chutes in situ in this application. Unfortunately, to create the window that we needed for CC4E, we couldn't salvage anything. It was good for us, it was bad for the Port Authority. We couldn't salvage any of the existing chute work to make the window for CC4E. So essentially back to an empty structure. We were able to mirror the 2 intermediate and spoon chutes to the original conveyors, and installed a rotating spoon diverter spoon, which then loaded onto CC4E. So I wish it was easy as these slides, you know, you just make a model, it all happens. There's a lot of work in a short space of time to make this happen. Yes, you can see it looks quite tidy, much better than the circuit boards, I can tell you. Stockpile 11 was the last 1 and 3 transfer to be done. In concept, the rotating spoon diverter is a relatively simple device. Material comes off the hood and just hits this rotating spoon, which can be rotated to any one of 3 positions. So that allows very easy realignment of the diverter. All of the forces of the stream flowing out of the rotating spoon are held by this bearing cartridge. So the drive down the bottom doesn't see any of those forces. It's just got a simple job to do, turning that spoon from one position to another. And it's only a half kilowatt drive. So yes, it's a very congested transfer tower, but like I said, far better than the alternative. That's just a view. The rotating spoon diverter in the centre feed, you're showing you feeding onto CC4E. And that's the overall run of those 8 stockpiles. The next thing that we looked at, and it's out of sequence of the construction program, but obviously the bulk earthworks that needed to be done for stockpiles 19, 20 and 21, if we want to move stuff around, that needed to be done earlier rather than later. So we did a review on stockpiles 19, 20 and 21, and also the transfer point that fed onto the skyline conveyor for those stockpiles. So we reviewed the layouts. We were late in the game. What we found was that the original designers that set out the transfer points hadn't allowed enough height to make control flow transfers. You could have transferred coal through it, no doubt, but wouldn't have got the soft loading benefits that the port was after. So would have seen high impact loads and minimal stream speed in the direction of belt travel. Port Authority confirmed that's what they thought they were getting in the first place. That's what they wanted, because now they've got 20 years of experience of control flow technology. They don't want to go backwards. So again, one of those bad news stories. Well, we needed to get more height in the transfer towers. The conveyors were at 15 degrees. We said, let us go to 18. We'd done it on the site before. We could get the headroom or move the stockpiles further away. Neither of those were acceptable. So what we ended up using was a rotating hood diverter. It minimised the height requirement. We did get to 16 degrees. That allowed us an extra degree in the conveyor lift, and allowed us to leave the tunnels and stockpiles where they were. So quite simply, the way this worked, there's a fixed trip in the reclaim conveyor that allowed the coal to either be fed onto the new 3rd stream shipping or back on itself to go over to the original 2 shipping streams. You see there, and that's the feed tube for stream 3 coming out of the page and back onto itself. The rotating hood diverter is room efficient because we start diversion as it leaves the head pulley. So as soon as it comes off the head pulley, we're directing it and at the ability to split where it's going. In the picture that's shown here, it's feeding onto the leg out to the 3rd stream conveyor, and if it was actuated up, it loads back onto itself. These aren't our preferred. Why don't you use this all the time? Well, you do have the complication of what do you do with your fines from your cleaners. You've got to then put a diverter system in for the fines. So that's why we would always prefer to do a fixed hood, get the fines back in the mainstream, and then you're diverting fines with the mainstream material. So if someone says, well, why don't you use them all the places? Because the fines is an issue. But you do what you have to do. This just shows a picture underneath that rotating hood with the intermediate going out to the 3rd stream and the spoon back onto itself. Over at Tower A, It's pretty much a simple process again, rotating hood and feeding the two shipping streams. Throw this one in. This is a very simple transfer for us. It's the one that feeds the skyline conveyor or trippers for the stockpiles. Again, we were asked to look at it. We end up doing the transfer for it. But at the end of the day, we could have built this transfer with 1.5 metres less head height. Not a big deal, you'll say, in a project of this size. It was too late in the process anyway to do anything about it for this project. But on a greenfield coal terminal that we reviewed, we took 27 metres of net height lifting requirement out of the terminal. 60 million tonne a year, 27 metres, you don't need to lift the coal going through it every year. So significant energy savings could be made. The last thing that I'll cover very quickly because it's a similar story to stockpiles 11 to 18 is on the reclaim for stockpiles 1 to 10. Again, went through the same process and decided it was the way to go. At this stage though, the project was quickly running out of money or was already over budget, and we would see it told, do what you're happy to put your name to, but do the least amount of changes that you can. So in this case, we maximised reuse of existing conveyors. The rotating hood actually provided a better envelope underneath it than the fixed hood on the other transfers. So that the fact that these transfers already had a rotating hood on them on stockpiles 1 to 10 gave us a bigger window, so we were able to capitalise on that. The existing chutes on these stockpiles 1 to 10 were up to 20 years old. They were inspected and found to be in a serviceable condition. So MHEA's designs were only limited to the in-by intermediate chute, but we reused it, we just modified it, and all existing chute work actuation was maintained, so very much reduced the scope of work on these conveyors. There's only one conveyor that couldn't meet the design tonnages because we were loading on the incline and the head height was greatly reduced, and that stockpile was the only one that was limited in its capacity. Okay, those shutdowns were completed in a 2-day period on each stockpile. I suppose what allows us to do what we do, the fact that we design, and we've been learning about how to design this now for a long time, the fact that we make what we design, and the results that we've got over the years of operation. We have demonstrated a 3.6 tonne reduction in belt cover wear. It makes sense. If you put material on the belt at the speed it's going, it doesn't need to drag it back up to speed. One of the chutes that we got from one of our customers, after 9 years it was upgraded, we got it back. No maintenance from SAP, not a single maintenance event in 9 years. The tile wear was less than 1 millimetre on average on that chute, and it had 130 million tonne of coal through it. Low noise. People are concerned about noise. We've demonstrated from 0 to 6,000 tonne per hour, our transfer noise of material flowing through our transfer 2.1 dPa. And importantly, when we hear a lot in discussions in the last day or so about dust levels, we've demonstrated a respirable dust level decrease from 3.66 to 0.39, nearly tenfold in respirable dust level in a coal transfer. So for RGT, what did they get out of this? Well, we got increased throughput, increased reliability. As soon as you take something, another mechanical device like a conveyor out of your network, you've got increased reliability. We've got a much improved plant layout, a simplified plant, 18 less conveyors. I'm saying at least 7, probably more like 10 million capital savings, reduced ongoing maintenance. And finally, I'd like to thank Mark Greenaway, the Project Director at GPC, Mick Wordsworth of MHEA, the original developer of our technology, Paul Sundstrom, who we still work with, Richard Morgan from Aspect, and Charlie Charlton and Matt Coco, designers at FLEXCO, all had a hand in putting this presentation together for me. Thank you.
Thank you, Bernie, for that fascinating presentation. Bernie will be back on the stage at the end of session 5 answering questions. I'd just like to thank Bernie for giving us all a world exclusive this morning, a softly spoken Australian. I'd like to now invite Andrew Stevenson to join me on the stage, please.